All right, here we go. Good morning, everyone. Thanks to everyone for being here again on this Wednesday morning. It's supposed to be hot out today, like 90 degrees. Those of you that have practiced outdoors today, stay hydrated. Today we are going to probably finish up the appendicular skeleton and move into a short unit on joints. This works out well. These are the two topics that you'll see in your lab next week. So we're back to being more synchronous between lecture and lab. We'll cover the appendicular skeleton and we'll do some work with joints on Tuesday next week. Also, before we get into it, also Tuesday next week in the afternoon, we'll have another speaker for our biology seminar series. I'm really excited about this one. So this is someone who's done some great work in lizards, and she's going to be out for a couple of days visiting and giving our seminar. Those of you that are in different clubs and organizations, if you could spread the word, I'd appreciate it. I can send you like a PowerPoint of this and like an image. But yeah, it should be a great talk. She's done some great work, and there will be snacks. So come check it out. For today, oh, look at that. For today, Wednesday, question mark. Yes, we're going to answer that. It's yes. We're going to first review your question out from your ticket out from Monday. And then I want to share something with you that's not human anatomy in the news. I'm not going to ask you questions, but I stumbled upon this article this week and I've just been completely fascinated by this. And it directly pertains to what we've been talking about in class, the world of leg extension surgery. I just have to share it with you. We're going to finish up the coxal bone and then talk about the lower limb. And then I have a quick review activity. You won't be drawing for this one, believe it or not. And then we'll get into joints as much time as we have a human anatomy in the news, remind you about exam 1, and ticket out at the end of class today. So kind of a long agenda, but most of the items are pretty short. Before we jump in, questions? All right, on Monday, on your way out of the classroom, I asked you the question, with what bones does the coxal bone directly articulate? You can see a diagram of your pelvic girdle here. And most of you got this right. The correct answers are with the femur. And so the left and the right femur. And of course, that articulation is here at the acetabulum. And we'll talk about what's at the femur end of that articulation today in class. The sacrum. So we have two sacroiliac joints here and here. Remember, these are very tightly bound joints that don't allow a lot of movement, but that's where your pelvic girdle directly articulates with your axial skeleton here. And finally, with the other coxal bone at the pubic symphysis here. So the two coxal bones articulate with each other. So those are the correct answers. Most of you got most of those. Note that a good number of you also chose the coccyx. Although that's in there, it's kind of associated with the pelvic girdle. This bone right here does not directly articulate with either of your coxal bones. So the coxal bones only articulate, each of the coxal bones articulate with 3 other bones, the sacrum, the femur, and the other coxal bone there. Questions on that? All right, just want to make sure you understood that. Okay, so this is just a quick aside. I stumbled upon this article about leg extension surgery. So this is a thing that people are doing these days. That's a weird way to say that. This is a form of elective surgery that is gaining in popularity. From the article I read, it seems like mostly men who are unhappy with their height go in and have this elective surgery. And what they do, you can see an X right here, is they actually sever the femur. They stick a titanium rod through the femur. You can see it goes into the medullary cavity on either side. And then the rod is actually expandable, and they can control its expansion with magnets. So they can sew everything back up, and they have this device they can put on top of the leg. And once a day for 90 days, they expand that rod by 1 millimeter. So it increases your height, it can by like 90 millimeters, which is what? That's a couple, 3 inches. Yeah, 2 or 3 inches, right? And so what this looks like here in an X-ray is you can see like the before picture, the during picture, and the after picture is you can see by the height of the pelvic girdle here, how it can increase your height. Basically, it leaves you immobile for several months. You can't, like for 2 or 3 months, you can't walk and move around. And obviously it takes a long time for that to heal. And what it does is it expands your height here in the stylopodium of the leg, so between your hip and your knee, but not everywhere else. So you get taller there, but not in other places. And from what I was reading, it can make you look kind of disproportionate. especially when you're naked. I couldn't find any good naked photos of people with leg extensions, so you have to just use your imagination there. But they had some photos of fellas who had this done, and you can see how they're taller in stature there. So again, not on quizzes. I just had to share this with the class because I was just so fascinated by this. And having just gone through major surgery on both legs in the past year and a half, thinking about choosing to do that for aesthetic reasons, I guess I can't. It's hard to get inside the mind of other people, right? There's lots of reasons people do elective surgery like this. So I'm not say that in a judgmental way, but it was hard to imagine going through the trauma of this kind of surgery to be just a few inches taller. The last point I want to see, and I'll get to Sophie and Matt in a second, is that what I really love about this, it really illustrates the dynamic healing capacity of your bone. So you can actually sever the bone here, and actually this bone will grow back to its entire length eventually. Of course, it takes a lot of time to do that and to build up that tissue, but just illustrates again how kind of impressive the bone is in regenerating and healing itself. So I'll leave you with that. A couple of questions, thoughts, Sophie, go ahead.
And like your skin and everything that's like in your legs.
Yeah, so what about all the other tissues associated with that? And so that's the reason they do it a millimeter a day, to allow those tissues to expand with the leg. But apparently it's excruciating painful. It's basically, what the article I read, you're basically laid up in bed immobile on all types of painkillers for like several months because it's just super painful because all those tissues are getting stretched to their limit and have to heal each time as well. I can see by your face that you're not going to do this anymore. Matt, go ahead.
You get a 5-inch height difference in the addiction, that's straight off.
Yeah, well, hopefully not the addiction, but yeah, and it's like 2 or 3 inches to be clear, not
Well,
yet.
I think one question was like, yeah, is there any way to combat like the muscle atrophy at all through like the 3 months of not moving your legs at all?
You would need to just go do physical therapy and exercise and get that all back. I mean, after 3 months of bed rest, you lose all kinds of muscle mass. So,
Yeah.
say again, Julie? Yeah, you can see like it's just elongated. Yeah, and that's actually, I didn't even notice that. That's true. You're losing all of that muscle mass because you're not necessarily because of the surgery itself, just because you can't move for that long.
So like your leg like compound leg movement would be affected like at the joints because of the titanium rod.
Yeah, they don't they keep it away from the joints, I think, for that reason. But yeah, go ahead. You know, I noticed that. I don't know. The article I read is just talking about the femur here. It looks like the exact same structure in the tibia, so I think so. Although what I don't know, and this didn't mention this in the article, is this would be complicated because you've got the fibula would have to expand. I don't know what they're doing there. They wanted to be even taller, I guess. So yeah, there it is. I had to share it. It was too much for me to contain within myself as an anatomy teacher. With that in mind, let's talk about more traumatic things that happen to the body. Last class, we talked about pubic symphysis diastasis. Remember, the pubic symphysis is the joint between your left and right coxal bones. Anteriorly, it's bound by this tough fiber cartilage. It can become damaged, especially during childbirth. You see an X-ray of an example here where it's kind of pulled apart. Now remember, there can still be these stretched ligaments attaching here that aren't showing up in the X-ray. So it's not necessarily that it's completely free-floating. It's just that those ligaments are severely distended. And the question was, what do you do if this happens to you? So I looked up a little bit. Basically, the number one thing is to take acetaminophen and stay in bed and rest. They generally try to be conservative with these kinds of injuries and just keep you from moving around and let it heal on its own. And over time, if it's not too severe, it will, those ligaments, or excuse me, the cartilage will kind of bring itself back together and will heal. Although, if you have suffered this injury during childbirth, you're much more likely to experience a similar energy with subsequent births. So often, if this happens during childbirth, women that then get pregnant again choose to have a cesarean section for subsequent births. Go ahead, Kat. Mm-hmm. That is not at all. Nope. I should be clear. That's the width of the cervix. So that is soft tissue, and that's independent from the bone for sure. And we'll talk about that. We'll talk about reproduction later in the semester. That's a really good question. In severe cases, though, they do have to do surgery. And what you can see here is actually, I don't know if these are surgical sutures or like a metal wire, but they in severe case have to go in and kind of bind it back together to hold it in place till it heals properly. So there you go. Great way to start your Wednesday morning. All right, let's talk about the lower limb. So as we mentioned in invertebrates with appendages, we have generally the two proximal parts of the appendage are referred to in general terms. So this applies to lizards and rabbits and whales and humans. We refer to the stylopodium and the zygapodium. In human terms, we refer to this as the thigh, is the upper leg, or the lower leg we refer to technically as the leg or shank or crus. I will try to avoid using the term leg because in the vernacular, when we say leg, we generally mean everything from like our hip down, right? In anatomical terms, the leg just refers to the part of the lower limb between the knee and the ankle. I actually like the words stylopodium and zygapodium because I also teach vertebrate anatomy, and then we use those for all kinds of different vertebrates. So you'll hear me use those words often in class, but you'll also hear me use some of these others, and your textbook will. So I do want you to know those. Now, the lower limbs are analogous in structure to your upper limbs, meaning they generally have the same floor plan, right? We have one bone in the stylopodium, two bones in the zygapodium. Then we have ankle bones, which are analogous to your wrist bones. And then we have the feet, which are analogous to your hands, right? However, the lower limbs serves a very different function than your upper limbs, and primarily because it carries the entire weight of your body, whereas generally you're not doing this with your upper limbs, some rare exceptions. So because of this, these bones are generally thicker and stronger than those of the upper limbs. The articulations of the lower limb as well generally serve the trade-off is in favor of stability over flexibility, meaning that these joints are more stable but a little less flexible. We talked about this in the context comparing your shoulder and the amount of flexibility you get because of that shallow glenoid cavity versus the hip, and the limited flexibility but increased stability you get because of the cup shape of that acetabulum in the coxal bone. We're going to divide the lower limb into three segments: the thigh or stylopodium, the leg or zygapodium, and the foot. And we'll walk through each of these in series, similar to what we did with the upper arms. Let me make sure you've got those notes. So let's talk here about first the articulation of the lower limb with the axial skeleton at the pelvic girdle. And this is your hip joint. And there's a couple features here that are important to note. The first is some anatomical terms that you're probably familiar with from lab. We have the head of the femur, which is this almost ball-shaped part of the end of the femur. And we have the trochanter, which is this structure here in the femur. It's the only bone in the body that has the kind of structure that we call the trochanter. The head of the femur, you can see, is this ball-shaped bone that fits really nicely into the acetabulum of the hip joint. You can see that in the diagram on the upper left there. Now, importantly, there is the joint articulates there, but it's also attached by this ligament called the fovea capitis. The fovea capitis is this ligament that attaches the head of the femur inside the acetabulum. And if you look at a femur, and you'll see this in lab, you can see this kind of little indentation here. Like if you look at just the head of the femur, it looks a little bit like a Death Star. That little spot there is where that ligament attaches to the head of the femur, and that just adds stability to that joint. Now, what's interesting to me is that during hip replacement surgery, they don't replace that at all, and it's just like the artificial head of the femur into the artificial cup of the acetabulum. And so I think that I don't know, I'm always surprised by the fact that you can still have stability in that joint without that extra ligament. But those of you with healthy hips have that ligament there. The femur is a really cool bone. It's the largest and strongest bone of the body. And as I said, it has this ball-shaped head that articulates with the acetabulum. and it's held in place there by this ligament at the fovea capitis. And I think I want to make sure. Okay, so actually, let me make sure I've got this straight. I think when I was describing this, I referred to the name of the ligament as the fovea capitis. It's not the ligament. This is just call this the ligament. I'm not sure it has an anatomical name. The fovea is this little indentation. Let me make that clear. That's the name of the feature on the head of the femur where that ligament attaches. It's not the ligament itself. I think I misspoke when I said that when I introduced it. The neck of the femur is the weakest part and is the part that where when you hear about a broken hip, this is usually what breaks. And you can see the neck around the pointer here. That's this part right here where it gets thin between the head and the trochanter. I think I mentioned this earlier in class in the context of osteoporosis and weakening bones, but what most often happens is because the bones are weakened and there's so much weight that's borne by the necks of the femur, that will actually break and then cause a person to fall, which is the opposite. Normally, we think of someone falling and the impact of that fall breaking that joint, but it's actually the other way around. It's actually the break that happens first, and then subsequently you fall because you can't bear weight anymore. Not all the time, but that's generally what happens when especially older folks suffer from a broken hip. There's lots of features on the bone. I'm going to talk about some and highlight some of them on the next slide. And they primarily serve as attachments for muscles. So you've got a lot of leg muscles attaching to the femur. So there's lots of terms on here. This is from your diagram. My next slide has fewer terms and the ones I really want you to focus on. So don't worry about copying down all of these at the moment. You have that image in your textbook, but instead I want you to focus on these. So this is a femur. Is it a left or a right femur? An anterior or posterior view? It's pretty tricky. We haven't talked about it yet. It is a right femur from the posterior view. So it's looking at someone who's standing like this. I want to just make sure it's clear too. It's disproportionate. I cut off like the middle part of the diaphysis here, just so I could show you the both ends of the femur on the same slide. Otherwise, it would be too long. So it looks a little bit disproportionate. Actually looks like they just cut it and insert the titanium rod here. Get leg extension surgery. Okay. There are some features on the femur I want you to know. The greater trochanter we've talked about a couple of times. It's insertions for a couple important muscles the hamstrings as well as the gluteus medius and minimus. Don't worry about the names of those muscles right now. I just want to throw out some terms so that when we study muscles later, you'll be familiar. Just know that they're attachment points for those muscles. The lesser trochanter is this guy right here down at the bottom, and that's where the what attaches the iliopsoas insert there. So those are muscles associated with hip adduction, so bringing your leg back together. We have the gluteal tuberosity, and this is this kind of line that goes down here, and that's the insertion of your gluteus maximus, so the largest muscle in your body. The linea aspera, so this gluteal tuberosity basically continues to kind of become this thin line that runs down the posterior of the femur, and that is the linea aspera. And a small muscle called the pectineus has its insertion there. That's another muscle in your inner thigh that helps you adduct your legs. So adduct, we'll talk about this in lab this week, but adduct is bringing together. And then we have the epicondyles on the medial and the lateral side. And here we have your gastric medius, so your big calf muscle has its insertion up on the distal end of the femur. So know those, 1, 2, 3, 4, 5 features on the femur for sure. And again, we'll revisit this in lab in the coming week. You'll see examples of this and be able to touch the greater trochanter and the lesser trochanter and get a feel for what those look like. I want to talk about development. Let me pause here, see what questions you have. Make sure you have a chance to get these notes. Okay, so we talked about these in lab, the epiphyseal plates or growth plates. These are the areas of the bone during development where new bone is created and the bone expands. And as an adult, when you're an adult and your bone stops growing, those plates become completely fused. But when you're young, this is actually cartilaginous. It's actually a joint here. And it's where cartilage develops into bone, basically, and the bone can expand. And you saw that in lab. I'm not going to talk about it in too much detail here. I just want you to see where, for example, on a femur, we see those results. Let's keep moving distally and talk about the kneecap, which is an example of what kind of bone? Do you remember this from earlier in the week? Sesamoid bone. So it develops in the ligaments. Kylie, go ahead. Mhm.
Correction, then like if there are other complications, would we do that surgery after?
Ah, really good question. Way to bring that stuff together. Yeah, so those surgery that I showed you earlier in an elective context, those can actually be done as well for not elective contexts, like congenital disorder or an early injury that creates one leg longer than the other, or things like that too. And I think that's actually where the techniques were originally developed. Wasn't just to help people get taller because they wanted to be taller, but rather to like address kind of the what's the word I want to use here? Address those kinds of congenital disorders or something like that. Yeah. Fun fact: I actually broke the growth plate on my my humerus when I was a kid, and they had to do surgery and like put screws in so it would go back together so my arm would grow. I did it when I was 4. So if they didn't do it properly, I would have my arm would have stopped growing basically when I was 4, but they did it. So I never have to think about it. But yeah, that's exactly what can happen if you injure your growth plate. Good question. Way to bring those just two things together. All right, so the patella is the kneecap. This is I like to think of this as a little helmet for the knee. It serves really 2 important roles. So it's a sesamoid bone, as I mentioned, and it's embedded in the tendons that secure the quadriceps muscles. So the quadriceps are the groups of muscles in your anterior thigh right here. And so you can all go ahead and feel your patella right there, commonly known as your kneecap. What it does is 2 important things. First of all, it protects your knee. So your knee is a very sensitive joint. And because of the way humans move through the world, we're often landing or falling on our knees. Anyone that's been around a young kid sees how much time they spend on their knees. Humans, we do all kinds of things where that joint needs to be protected, whether it's crawling or falling. And so it protects the knee. And secondly, it improves kind of the mechanical leverage of the thigh muscles across the knee. So it gives your quadriceps muscles better ability to extend your leg at the knee joint. And that's important for a variety of physical activities, especially walking and running. So 2 important roles of the patella: it protects the knee and improves the leverage of those those muscles over the knee joint. Go ahead.
So hyperextend the knee, does that like affect the patella at all?
It can, but it's usually not the patella that's injured. It's actually usually the ligaments and cartilages in the knee joint itself. The knee joint is set up so that it doesn't go past 180 degrees generally. And so if you hyperextend it, what you can do is stretch those ligaments, especially in the posterior of the knee. I'm not really showing this very well. I'll show you, actually I have some diagrams showing up. But it's usually the soft tissue that's injured, not the patella itself. Although you can like break your patella, you can crack it if you fall hard or something like that. We're not going to do too much with the patella. You'll see some examples in lab. One important vocabulary you should know is the apex is the point of the patella, and it's generally pointed, not generally, it's pointed inferiorly. Let's talk about the zygapodium of the leg, also known as the shank or the crus. We have 2 bones here. So again, these are analogous to the 2 bones in the zygapodium of your arm. We have a big tibia and a little fibula. Notice here that in the zygapodium of your arm, the radius and ulnar are about the same size, right? They're more or less parallel, they're more or less comparable. This is not true in the leg. In the leg, we have one really big bone and one really thin bone. And in fact, in other vertebrates, these 2 bones, the fibula becomes so small, it actually becomes fused with the tibia. And this becomes just one single bone, for example, in birds. All birds, most birds, at least most birds, maybe all birds, these 2 bones are fused. Anyone take ornithology and know if it's all or most.
Most.
Most. There's some that have the two bones.
Yeah, like, skeleton.
Oh, really? Oh, from that group. Nice job. Did you take ornithology? It's impressive. Good. Okay, so most birds, but not all. And that makes perfect sense if they're walking a lot, then they. Okay. Good job, Seth. So 2 bones you see there. This is the where here. This is the anterior view of a right tibia and fibula, and then this is going to be the posterior view. So the fibula is runs lateral to the tibia. So this bone is someone standing looking at you like this. This bone is the right leg, also someone looking away from you. And so we just talked about all of this. Yep, I just kind of talked about all this. The fibula is this very thin stick-like bone. What's important to note is it's actually not technically part of the knee here. You can see it articulates with the tibia proximally, but it doesn't actually articulate with the femur at all. The knee joint is just between the tibia and the femur, and with, of course, the patella in there as well. At the distal end, this does have a larger head here, and that serves to stabilize the ankle joint. And I'll talk about this kind of clamp-like structure that forms your ankle in just a moment when I get to the tarsal bones. Similar to the bones in the zygapodium of your arm, the tibia and fibula are bound tightly together by this interosseous membrane that keeps those 2 bones nice and parallel and snug together. They're best buds. At least that's how I like to think of them. Kind of suck if they weren't, because they're just stuck together. Lots of features on these bones. I'm going to show you a diagram with just 5 terms highlighted in red that I want you to focus on for the moment. The first is the tibial tuberosity. Remember, a tuberosity is kind of a raised, rough area on a bone. And in this case, the tibial tuberosity is important because this is where a lot of ligaments attach and anchor your quadriceps. So again, allowing your flexion of your leg at the knee joint. We have the head of the fibula here. You can see how it articulates with the tibia there, this very kind of tight joint. Then the last term I want you to know is malleolus. A malleolus refers to these kind of processes that stick out the distal end of the bone. Bless you. And we have a lateral and medial malleolus around each ankle. And the lateral malleolus is formed by the fibula, the medial by the tibia, excuse me. And these bones form this kind of clamp-like structure, because if right now you move your ankle, you can realize that you have a lot of flexibility in your ankle front and back like this, but you have much more limited lateral motion at the ankle. So this provides extra stability to your foot. When you're walking or running, it's really important that you can flex your foot front and back like this, because that's where you're getting all your power with each step. It's less important that you can have mobility side to side, although you do need a little bit. So these essentially act as clamps that keep those tarsals freely moving in one plane, but restrict their movement in another. And in fact, when you twist your ankle and you get what's generally referred to as a broken ankle, it's usually the malleolus that tends to be what's fractured. So here you can see malleolus fractured here. So knowing that this is a fracture of a malleolus, which bone is this one here? Which bone is fractured here? Tibia, and you can tell simply because it's larger, right? Yeah, and actually this one you can actually see slight fracture in the fibula, kind of more proximate as well. So let's see, I think that's all I want to say about the structures on those bones. There's a lot other details here that I'm just not going to get into in lecture. I just want you to know the major components of these for lecture. I think I saw a hand. Did I have a question? Okay, so we talked about that. Let's talk about the foot. I know we're cranking through, but there's really not a lot of new information here, given that you've seen all this with the hands already. Similar to the hands, we can break the bones of the foot. I shouldn't say break. We can categorize, that's a better way to say it, the bones of the foot into 3 groups: the tarsals, which are analogous to the carpals. So these are your ankle bones, the metatarsals, and the phalanges, right? Exactly the same as the foot, those 3 groups. We have 7 tarsals, 5 metatarsals, and 14 phalanges. I'll show you those in just a second. You don't need to memorize those numbers. I'm just kind of giving you a count for how many bones are in the foot. The foot has 2 primary important functions. The first is that it very obviously supports the body weight. All of the weight of your entire body is transmitted down to your 2 feet, and specifically 2 kind of small areas that come into contact with the ground, generally speaking. So they bear a lot of weight. And secondly, the feet act as a lever, and I talked about this just a second ago, talking about the ankle joint, whenever you're walking. And humans are remarkably adapted for locomotion via walking, and especially long distance running. So 2 things that humans are really good at, that are very closely related actually, is long distance running and sweating. And those 2 things are tied together because when you're long distance running, it's really important that you're able to sweat and cool your body. And that's how a lot of humans are able to hunt so successfully, is they're not bigger, they're not stronger than a lot of animals, but they can actually outrun animals over long distances. And long distances, I mean kilometers and kilometers and kilometers. They can basically run wild game until it's exhausted. And what happens is oftentimes some of those animals will overheat, whereas humans can sweat and stay cool. Animals overheat, and they can basically just chase them till the animals become exhausted and can't run anymore, and then they can get up. So yeah, we're really good at those things. One last thing about the structure of the foot is the fact that we have these segments of bones that all lie horizontally on a plane with the ground. So not all vertebrates have all of these bones in contact with the ground. In fact, if you looked at like a cat's paw, the metatarsals of the cat are actually like above the ground, and it's only the phalanges that form the paw that come into contact with the ground. So they have a different kind of leg structure than we do. But as humans, our tarsals, metatarsals, and phalanges are all on the ground. And this allows us a lot of extra stability and balance when we're walking on uneven ground. So it's only in very recent human history that we've spent most of our days walking around on flat surfaces. In fact, in the past, we'd be walking around on a lot of uneven ground, and having these this ability to flex the foot and maintain your balance on the ground is really advantageous.
When they do contact, it's even off the phalanges, right?
I don't know how much it would be. So the claw extends from the end of each of the phalanges. I don't know how deep they go. I don't know if they actually get to the bone or not. They do get to the bone. Oh, they okay. So then are you left with like a bunch of little claws with like the most distal phalanx from each bone, or each? See if you can save one next time. Be interesting for class. Actually, it would be interesting to see how that claw attaches. But yeah, each claw kind of, and that's those structures are homologous to our fingernails. It's the same. It's keratin. It's the same material as our fingernails. Kitties. Okay, let's talk a little bit about the ankle bones. There's 7 bones. I'm not going to ask you to memorize all of them, although in other human anatomy classes, other contexts, you might need to know them. I want you to know 2 in detail and be able to identify them. And again, we'll look at this in lab. And those are the talus, which is the kind of most superior bone here. This is the bone that articulates with the tibia at the ankle joint, and the calcaneus, which is your heel bone, which is this big old bone right back here that forms your heel. You have this calcaneal tuberosity. So this is a connection point for a lot of tendons that attach to your calf muscles. And this is where what's called your Achilles heel. This is the tendons that run up the back of your heel. They don't have socks on. But anyone that's injured that this set of tendons knows that they're really big, strong tendons. And if they get injured, it can be really painful and take a long time to heal. I have the names of some of those other bones there. I'm not going to get to that level of detail. I just want you to know the talus and the calcaneus.
Does that bone being called the talus have anything to do or any relation with the word talon in birds?
Oh, I don't know. I've never thought about that, and I don't know the origin of this word. Wait, would I look that one up? It could be possible, because that's similar. Yeah, I could guess, but let's look it up. And then finally, I just want to talk about the phalanges. And well, I guess I kind of glossed over the metatarsals a bit, but the metatarsals and the phalanges, similar to the hand, they're numbered 1 through 5, and the same as in the hand, we have 2 phalanges in the first digit. In the foot, this is your big toe and called the hallux. So this is again analogous to the pollex, your thumb in your hand. So notice there's only 2 bones here, 2 phalanges here, and then the rest of them have 3 phalanges. And the last tiny distal phalange is really, really small, especially in your little pinky toe or digit 5.
Evolved out of the prehensile feet.
When did humans evolve? Oh gosh, well, not that long ago in evolutionary terms, somewhere around 4 or 5 million years ago, which is a long time ago, but it would come because our most recent common ancestors were very arboreal, and even some early hominids were arboreal, things like Australopithecus and things like that, where did a lot of climbing. And so that's actually one of the ways that you can see is that in those early humans, I'll call them humans, the pollex is more thumb-like than big toe. But over time, basically, humans got really, really good at running and walking long distances and not as good as climbing. And so that put pressure, selective pressure over evolutionary time for the bones to take on this more parallel structure rather than have one of the digit pockets.
That big gap between the phalanges and all of the bones that are there. I was reading something recently where people wear 2 types of shoes. Their toes are close together, and their feet are actually starting to grow. Their toes closer and closer together. It seems really, really bad.
Yeah, I mean,
Start to form and kind of curve down.
right. I know that modern footwear can cause a lot of problems as your feet are in them for hours and hours a day, but it could be all kinds of different things for sure. You get bunions and stuff like that.
They're the same word.
They are the talus and talon. No kidding.
Talus, it's ankle bone. And talus is-
There you go. Now you're always going to remember that bone too. Good. All right, this is perfect timing. Let's wrap this up here. I want you to do a quick activity. You're going to work with another person next to you or groups of 3 if we need to do that, depending on how even and odd our numbers are today. And I want you to make a Venn diagram. And actually, I made a mistake here. I should have capitalized. So Venn is named after a person. It should be a proper name. So I should have capitalized the word Venn there. Don't tell anybody that I made that mistake. So I want you to draw a diagram that looks like this. And then I want you to fill in characteristics that are unique to the hands, but not the feet. Characteristics that are unique to the feet, but not the hands. And then characteristics that are common to both. And I started you off with one thing in each category. Go ahead and convert. Each of you should draw your own diagram, but work with each other and just see how many things you can brainstorm on that list. I'll go around and check in and just see, and let me see who you can work with here. Let's do this. Sophie and Jessica, you guys are together. How about so we'll work for Holly and Zoe and then Mark and Huddy, is that okay? And then let's see, we can do a group of 3 in the back. Or you can just do 2 groups of 3 back here. That works for you guys, and then you guys can go. Each draw your own, but just brainstorm, share your ideas with each other. You know, I like Venn diagrams.
Yeah.
All right, there's obviously lots that can go on this list. I just wanted you to start kind of brainstorming some. You can go back and revisit this. I guess could you? Do you, well, show me, get real quick, just show me the number of fingers corresponding number of minutes you'd like to finish this up. Just debating what else I want to cover today. Okay, let's take one more minute and do that, and then I'll skip one thing I was gonna do. We'll do it Friday.
Oh, it's like, yeah, never mind.
All right, let's bring this back. I just want to make a couple announcements. I have a human anatomy in the news, but I'm going to skip that for today. Again, it's on your program again for Friday. I'll just talk about it on Friday, but it's about the sesamoid bones in your knees and how people nowadays have them more often than they did in the past. So we'll finish up the appendicular skeleton and talk a little bit about get into joints on Friday. So just as a reminder, your exam, this is all information you have already, so I'll just offer some refreshers. Your exam will be on Monday. We will not meet during class on Monday. Instead, you'll have that time to work on your exam. I've designed it to take 50 minutes, but you'll have 70 minutes again to take it. So you can do that whenever suits you. I'll have it open from 7 a.m. to 11 p.m. this coming Monday. It will cover everything we've covered through today. So it'll cover everything from the first day of class through the phalanges of the lower limb. We will not talk about joints or anything like that on the exam. I don't want to put things on the exam that we're just covering on Friday. Just as a quick aside, unfortunately, I'm not going to have open hours on Monday. So you'll have that time. Well, not you'll have that time. Unfortunately, I won't be there to consult with on Monday during the exam. One thing I want to emphasize is if you're doing this exam or any others for this class and you have a technical difficulty, Blackboard doesn't load an image, something doesn't save, something like that, please don't fret. We will work it out and we'll make sure that it's all good. In the past, when those things have happened, I know students get really worried, like I'm going to get a 0 on this or whatever. That will not happen. We'll figure it out. So if that does happen to you, of course, let me know and just know that we'll solve it in a way that works for you. I don't want you to be stressed about technology because that crap happens and it's something we can deal with. And I don't want you to feel stressed about that. So with that in mind, remember, Danny has a tutoring session on Thursday, tomorrow night. in the Ice Cube room at Beagley Library. And unfortunately, and our class exam is Monday, so we won't be meeting on Monday. With that, I just have a quick ticket out. You can upload your Venn diagram and answer one question for me. And I will see everyone on Friday morning.